Okay. Hello, everyone. Good afternoon. My name is Shreya Anand. I will be the chair for this session. This is the Transients and Variable Stars session, and we'll have a number of contributed talks today. So I'll start off, and Tomas Ahumada here has kindly volunteered to moderate the Zoom and Slack for questions. So a few reminders. The uh, about the code of conduct. Harassment and unprofessional conduct is not permitted or tolerated. So if you experience this or witness this, please go to the RCW code of conduct contacts, which are listed here. And a few logistical reminders as well. So virtual participants should be muted when they're not speaking. In-person participants should speak into the microphones at all times because otherwise you will not be heard by folks on Zoom. And alternatively, the chair can repeat these questions into the microphone. So please, if you are online, use the Slack space for question and answer and further discussion. Also, in-person participants can use the Slack channel for further discussion. In Zoom, please preferably request to unmute to ask your question. We prefer if you don't use chat as much. You can pose questions in Slack as well. And if needed, you can also raise your hand in the Zoom. All right, so we'll start with the first talk from Paul Schechter on the non-simultaneous flashes of quadruply lens supernovae, discovery, precovery, and recovery.
Thank you, Shreya. I've got 7 minutes to tell you about quadruply lensed supernovae and the challenges associated with them. The working hypothesis for this talk is that the configurations that we see of quadruply lensed supernovae will look very much like the first quadruply lensed quasar, PG 1115 plus 080. The hosts of the supernovae are likely to have similar configuration, and the supernovae themselves are likely to have a similar configuration. So think PG 1115 plus 080. Now, perhaps, of course, you're not familiar with this, so that you can think it, let me show you what it looks like. It's got 4 images. Is there a pointer? It doesn't matter. It's got 4 images. This is a HST medium band infrared, near infrared. You can see that there are 2 bright images with fluxes normalized to the image at the bottom of 2 that are roughly 1 and 2 that are roughly 0.25 or 0.2. And so those 2 images are very much brighter than the other 2. You don't see a flash or any change at the same time. You see them at different times. Time delays are a crucial part of gravitational lensing. The first image to brighten, if there's a supernova, will be the one at the top at time 0. And then A1 plus A2 are very close to each other. This entire field is 3 arc seconds across. The separation between the largest separation is about 2 arc seconds. This is typical of what we'll be looking for. And so the 2 brighter images are the ones that you're most likely to see because they're the brightest. So what that means is that for the image on top, when you first discover the supernova on the 2 images in the lower left, the first image has already reached its maximum or something close to it 9 days before. And so you have to go back to that position and do your photometry as well as you can with whatever you have. Then another 10 days later, or 9 days later, the lower right image goes off. So that's the recovery. And that image is generically the faintest image, and that recovery is going to be the most difficult thing. So you would like to know where to look for the precovery, and you would like to know where to look for the recovery. The better you know where to expect them, the better job you can do of forcing your fit to the position where you know it should be. The one thing I didn't say that I should is that lens supernovae will not look like this, in that for lens quasar, the quasar images are very much brighter than the lensing galaxy, that faint smudge at the center is the lensing galaxy, whereas the lensing galaxies for lens supernovae will be brighter than the supernovae, and that'll make the photometry a bit more difficult. Let me get on then with some of the challenges. I mean, if this isn't challenging enough, things get worse. And what makes things worse? First, let's suppose that the host has exactly this configuration. That's great. We can make a model for that and come prepared with a model, knowing what this lens does. However, the supernova may not be at the center of the host galaxy. And the host, and something is quadruply lensed only if you land inside something called a diamond caustic, which is small. It's about 10% or 20% of the biggest separation. And so if the supernova is too far off from the center of the host, even though the host is quadruply lensed, the supernova isn't. Shucks. But if you've got a model, you can compute, if you see the supernova, seeing where the host is, because you have pre-images of the host, you can figure out where the supernova lies with respect to the host, whether or not it's inside the diamond caustic, and whether or not this is actually going a quadruply lensed supernova. Of course, that means that you have to be able to make a model for a gravitational lens on the fly. Some of you may have friends who compute lenses, models of gravitational lenses, and you know that they sit around for days waiting for their programs to run on big clusters. And so you think you really can't possibly hope to do modeling on the fly. The good news is, yes, you can. There is a model for quadruply lensed systems that puts the four images of the quadruply lensed system at the points of intersection of an ellipse with a hyperbola. It's like Keplerian ellipses compared to elliptical integrals. You don't think about the elliptical integrals, you think about the geometry of Keplerian ellipses and equal areas. It's the same idea. The images form where they intersect each other. I could show you dozens of these. I've got dozens of these, but they work. They're not the ultimate model, but good enough for the work we do here. And then, making this even better, is that an undergraduate student of mine found the first exact forward solution for a quadruply lensed system. Forward means you go from the lens parameters to the images and not vice versa. So there's no iteration involved. It is so simple that I can show it to you in one equation right here. That's not, the theta is the position, angular position of the image. And this is interesting. It's got two square roots in it. That's because it comes from a quadratic. It comes from a quartic. And the quartic is a quadratic of a quadratic. And so there are two plus or minuses here. So you evaluate this expression for each of the plus or minuses. So there are four possible solutions. And there's some other things about what these numbers are. There's something in there, U, that you have to solve. The important thing to remember about this particular thing is that the time to compute a model compared to what Keaton takes. Keaton has a program to model lenses. Keaton's program takes 850 milliseconds to compute this model. Fowler's method takes 1.9 microseconds. So you can compute this on the fly and make your models. Of course, you have to use it. So the challenge is going to be whether or not we can find the positions of the where to look backward, for the supernova when it first went off in the first image and where it's going to be in the second. And we've got something that will make your life easier if only you will try to understand it. That number is 400,000 times faster.
Okay, thank you so much for your talk. Please pause. Okay, so now we'll take some questions from the audience. Yes, go ahead.
Hey, Paul, this is great. This only is valid presumably if the lens system is fully resolved. Do you have a sense for how many systems are going to be fully resolved if they're galaxy supernova lenses versus unresolved in LSSC?
So the paper that everyone uses is Oguri and Marshall. I've told them I think it's wrong, but that's the paper that everyone uses. I think in particular, most quadruply lens systems are going to be quadruple by virtue of their being in quasi-cluster environments. I had a student who wrote a paper, what causes quadruply lens systems to be quadruple? And the answer is not the ellipticity of the lensing galaxy, but the tide from something nearby, and it has to be a big tide. Gil Holder and I wrote a paper about this 20 years ago. You don't get quads without big, strong tides.
We have time for a few more questions. Does anyone have any more questions? Yes.
So you hinted that this forward solution, this exact solution, requires some assumptions that turn out to be pretty good. But I wonder if you could just elaborate a little bit more, or maybe I misinterpreted the hint you were dropping there.
I could talk about this for hours. Yes, the particular assumption is a flat rotation curve for the galaxy, and singular, and that is the one that, and that the equipotentials are similar ellipses. And flat rotation curves aren't a bad guess. Whether or not they're similar ellipses is actually trickier. And it doesn't work for multiple systems, double galaxies, it doesn't work. But 90% of the systems lensed by galaxies are lensed by single galaxies, or pretty much single.
Okay, I think we have time for one more quick question. Is there anything on Zoom? Okay. All right. Seeing nothing. Let's thank again Paul for his talk, and invite up Riley Clark to talk about measuring the temperature profile of an M dwarf flare with DCAM and the future of flare studies with LSST.
Yeah, I'm sharing my screen. Okay, thank you. Okay, hi everyone. My name is Riley Clark, and this summer I completed my PhD at the University of Delaware, and thank you very much. So today I'm going to tell you about a part of the work I did for my dissertation, in which for the first time ever, we have measured the temperature profile of an M-dwarf flare using single band photometry by taking advantage of differential chromatic refraction. And I'll also talk about how we expect to be able to do this for the huge volume of flares that Ruben will detect over the next 10 years. So stellar flares are stochastic bursts of electromagnetic emission that occur on stellar atmospheres, and this emission ranges all the way from the radio to the hard X-rays. And in optical light curves, flares have a very characteristic shape. It's a fast initial rise followed by an exponential decay, that takes place over a course of a few minutes to a few hours, like we can see in this inset of the light curve of Proxima Centauri. But while we know a lot about the photometric morphology of flares, we know a lot less about the constraints on how the temperature of the flare evolves over its lifetime. And it's important that we obtain a large sample of flare temperature measurements in order to inform models of the physics of energy release in stellar atmospheres and the impact on exoplanet atmospheres, where the ultraviolet radiation from flares can strip ozone from atmospheres and render these planets uninhabitable. So what do we actually mean by a flare temperature? Well, flare temperatures are typically measured in one of two ways. We can measure them from a ratio of fluxes in two different filters, or by directly fitting black bodies to observed flare-only spectra, like in this example on the right. But the first method requires either multi-band observations or serendipitous overlap between multiple surveys, and the second requires dedicated spectroscopic monitoring campaigns. And so this means it's really hard to obtain a large sample of flare temperatures across a broad population of host stars. Fortunately, we are on the cusp of a new era in large-scale time domain astrophysics with Rubin. So how many flares do we expect Rubin will detect? So Hilton et al. 2011 estimated the flare rate in LSST U-band, and they expected between 5 and 25 flares per U exposure at low galactic latitudes, at galactic latitude 20. However, they assumed that the U exposures would be 15 seconds, but now that's been updated to 38. So we updated this estimation and expect around 2,000 flares with a change in U magnitude above 0.1 mag per U pointing, which we extrapolate to on the order of 1 million flare detections over the 10-year survey. But unfortunately, even though we expect this huge treasure trove of flares will be detected, they will be detected very sparsely in wide, fast, steep. We expect that only due to the wide, fast, steep cadence, these flares will only be detected in 1 to 2 data points at most. So on paper, that means that Rubin is actually really terrible for flare studies. You would never use a survey with a cadence like this to study M-dwarf flares, unless we get clever and figure out a way to extract some kind of information from an event that is only detected in a single exposure and a single band. And so to do this, we can leverage differential chromatic refraction. So this is an atmospheric effect that is an apparent shift of the source location towards the zenith of the observer, and it's a color-dependent effect. So it depends on the air mass, it depends on the spectral energy distribution of your source, and it depends on which filter you're using. And this is something that has to be corrected in order to ensure accurate astrometric solutions and remove biases from galaxy shape measurements in weak lensing models. But there is actually precedent for its use in astronomy. It's been used to improve redshift estimation for extragalactic science for quasars and SDSS, and it's expected that it'll be able to do similar things for quasars and supernova in simulated LSST data. But the idea for flares is that because the red quiescent star will experience some amount of DCR, refraction due to DCR acquiescence, but then during the flare, we expect that the whole source gets bluer due to the hot flare emission. And so you get a small excess in the normal amount of DCR that you see during quiescence. So if you can measure this very small positional offset that only occurs during the flare, we can infer a color temperature even from a single band detection of the flare. And so last year, we published a paper that explains our expectations for whether or not Rubin will be able to resolve these small positional offsets under various observing conditions. And we found that Rubin is more than capable of performing this type of study for many different temperatures of flares over a wide range of different air masses. But this year, we showed for the first time, we actually performed this measurement for the first time on data similar to the data that Rubin will produce. So we used data from the dark energy camera to, for the first time, measure a temperature profile using this method. And it just hit the archive today, actually. So, and I'll show this QR code at the end as well. So we use data from the Deeper, Wider, Faster program, which conducts multi-band and multi-messenger observations on millisecond to hour-long timescales. And the optical components of this are high cadence exposures with the dark energy camera. And because as part of this program, DECAM has to observe simultaneously with telescopes in Australia, they tend to point very low on the horizon, which means higher air mass, but that's actually good for our science case because air mass enhances DCR. And Sarah Webb published a paper, a collection of flares that were detected in the Deeper, Wider, Faster program, including this 6 magnitude flare on an M7 dwarf. So this was kind of like a perfect poster child for doing this type of study. So our objective here is we want to measure the amount of delta DCR in each epoch and convert it to a temperature over the entire night in which the flare was observed. But how do we actually measure this DCR on image data? So what I'm showing here is an animation of just a cutout centered on the flare star. And at each time step, there's this vector centered on the star that is pointing from its location, its position at the beginning of the observing period to its position at that time step. And so it's the color of this arrow is such that when the star is moving towards the zenith, which is what we expect for DCR, that arrow is colored white. So before the flare, we just kind of see it bouncing around, just jittering due to astrometric noise. But then once the flare happens and it brightens, that arrow pretty much stays pointed towards the zenith, which is what we expect for, which is exactly what we expect since the source moves towards zenith when the flare happens. Okay, and then when we zoom out to the entire DECAM CCD, I'm just showing this to show that we are also tracking this value for 92 other stars in the CCD. So we're tracking, explicitly what we're tracking is the projection of this vector onto the zenith direction. So just the dot product between that vector and a vector pointing towards the zenith. And so this is the data we get. So the top is the light curve. The middle is this projection that we're measuring, which is how we quantify the DCR. The gray is the average and standard deviation of all of the reference stars that we compare to. And then the bottom panel is the detrended measurement of the flare star DCR. And then finally, we convert that measurement to a color. We convert it to an effective wavelength by solving this equation in each epoch. And so then we get these two flare observables. Since we're performing PSF photometry on every epoch as well, we get the flare light curve on the left, and we get this effective wavelength measurement on the right. And then we use these two observables in tandem to jointly forward model the temperature over each epoch of the flare. And so when we do that, we get this temperature profile. So the temperature profile on the top, we do this forward modeling for different constraints on a geometric property of the flare called the filling factor. And we show that our model solutions become much more stable and more constrained when we control how the filling factor evolves over the flare's evolution. And then we also compare two different models, one of which is a continuum-only SED, and then the other model includes emission lines, specifically calcium and Balmer series emission lines in the SED model. So there you have it. There's the first constraint on stellar flare temperature from single band photometry. All right, so I'll leave you with some takeaways and a link to our paper and stop here for questions. Thanks.
Thanks very much, Riley. I think we have time for one quick question, just one. I saw your hand.
So congratulations on finishing in the paper in the archive. I guess I can imagine there'd be a systematic if there's a blend of two stars, one of which flares, you'd get an astrometric shift. And if that's true, it would be advantageous to do this on difference images.
Yeah, I think that's a good point. I think Fortunately, in the case that we did this for on the DECAM data, it was not particularly crowded. So I think we weren't too worried about blending of stars in that case. But yeah, for wide fast deep, especially at low galactic latitudes, that might present more of a concern. Oh, okay, I see what you mean. Yeah.
Okay, thanks very much, Riley. Let's thank Riley again. And if you have questions, please ask them in the Slack. So now we'll welcome Dave, Dave Sand talking about shadowing LSST, extremely early supernova discoveries in the nearby universe.
Recording in progress.
Works for me. 2-minute warning. All right. Thank you so much, everyone. I really appreciate you having me here. I'm a LSST non-user. I'm a normie. Okay. So today I'm going to talk about a new project for you where we are going to shadow LSST with DECAM. This is a new survey program recently awarded time from Noir Lab that will be ongoing for the next 3 years. The idea is the Wide Fast Deep survey has a 3-day cadence, and we will fill in those days in between with DECAM. Hide the participants. I would love to. Can I do it like this? Okay, all right. So the idea, shadow LSST with DECAM. You got it. Now, why do I want to do this? I only want to find a few supernova very, very young. Okay, there you go. So this is my very short diatribe where we in the transient community, we find thousands of supernova now. So those are great for statistical studies. They may not have the best data sets, but you could do a lot with them. Slightly higher up on the pyramid are individual objects where you get great data. You could write a single object paper. We all do this, right? But then at the very tip of the pyramid or the tip of the spear is the objects where you get truly exceptional data, where you're testing models, you're observing things you haven't seen before. It's not quite this Tony Tyson unknown unknowns, but it's more like a directed known unknown, okay? Where if we get excellent data, you will see things that you haven't seen before. An example of that is here in the lower left, this supernova 23IXF, very famous core collapse supernova in M101, okay? You can see in the very early data, the first day there's an extra little hump that doesn't fit the line. That has not been seen before because we do not find supernova at such low luminosities. Now, you will be able to do this quite often with LSST if you have the right cadence. So I have some bars there. The LSST Virgo cluster single epoch depth is like off the charts at the bottom, extremely faint. Even with DECAM at 100 megaparsecs, you're still able to discover young supernova like this and see that early signature that we've literally never seen before. So we will see this much more commonly. I've wasted half my talk already. We've been doing this now for a few years on a much smaller scale with a 16-inch telescope. It's the DLT-40 survey, where we only look at galaxies within 40 megaparsecs because these early signatures, this absolute magnitude there, We could only see those with our small telescope out to 40 megaparsecs, but we would observe these galaxies with a 12-hour cadence, okay? Here are some of those signatures. Obviously, I don't have time to get into that, but they last a very short amount of time. Now, with LSST, we will be able to observe these signatures up to literally 100 megaparsecs. You'll get dozens of examples if you're really finding these supernovae very young. Okay, I'm just going to flash you some of these signatures that we think we'll be able to see. Sometimes we've seen them a few times, some we haven't seen before, okay? So on the left, for a type 1a supernova, if you have a normal star and your white dwarf and it explodes and hits that normal star, you expect to see a little shock within the first couple days, but only the first couple days. You see that for different companion stars there. There are other models. If there's a little bit of circumstellar medium, you might see a signature on 1-day timescales. If there are nickel clumps, etc. You could see things on 1 or 2-day timescales. Now, we actually see these things in a handful of cases, and they look quite weird and quite different from time to time. Over here on the far left is a very blue little bump. Here on the right actually is an extremely early red bump in the inset there. A lot of times we basically don't know what's going on here. We want more data like this. 2 examples is great, but we really need to start building up a sample. There are even early velocity signatures. Here's another 1A where we caught it within hours of explosion. Its velocity, its silicon velocity there is over 30,000 kilometers per second. Within a day, it's at 24. We don't know what happens within that day or why it's at such high velocities. Again, that's something that hasn't been seen before. And we want to make it more routine in the LSST era. There are spectroscopic signatures in core collapse supernova that also change on a same night time scale. You can see that here, especially that C3 line. It's in a matter of hours, these things disappear. So let me just talk to you about our program very briefly so that I have enough time. So wide, fast, deep has a 3-day cadence, okay? Obviously, we cannot cover the whole LSST sky, so we have to be strategic. So night 1, we observe a nearby galaxy cluster filled with LSST. Night 2, night 3, we observe those fields with Decan to find extremely young supernovae, okay? If we find something, we have SOAR TOO time. Actually, we have TOO time on many telescopes, but as part of this NORLab program, it's all integrated there. And then we go on with our worldwide response. And so the idea is in these select fields, basically to maintain a day cadence for the next 3 years. Gulp, okay? Now, again, remember this principle. I do not want to find a lot of supernova. I'm like the opposite of everyone else. I only want to find a couple dozen over the next 3 years, but each one has exquisite data. We'll press on the models and will hopefully teach us new things, okay? Oh, do you want to join? Just send me a note. This is an open program. I'm not like one of those guys. Like you should just join our, you should just join our project if you're interested. Thank you. Here are our cluster fields, if you're interested. I actually noticed a typo while I was staring at this. So just be a little careful, but this is more or less our plan, okay? Virgo cluster is going to be very exciting. I'm really excited for spring Virgo cluster alerts, perhaps. We talked about Virgo cluster earlier. And here's just another plot showing actually, even beyond this project, you should think about shadowing LSST to do your science if you need to do things on short time scales. I think it'll be a lot of fun. And you could find a lot of things that, I think will be very rare, kind of Tony Tyson light unknown unknowns, right? Thank you. That's it.
Deep. Thanks so much, Deep, for the great talk. Any questions? Maybe while people are thinking, I'll ask a question. Oh, yes, go ahead. So I see a question on Zoom from Saurabh. Please feel free to unmute.
He's my collaborator. He better be nice. Yeah.
Great talk, Dave. This is actually kind of a question or comment for the people doing alerts and brokers. Dave, if you go back to your slide showing the 4 days, you see in that first day, it's a non-detection from Rubin. And I think this is going to be a real problem. How are we going to know that Rubin did not see something on night 1? right? We know when it gets an alert, but how do we know that it did not see something and to what depth? And I think that's something that the alerts and the brokers, we're going to have to solve that problem. We would really like to know that there was nothing there, and we want, how will we know that?
I have half an answer, but I would love a real answer.
Obviously, we cannot predict that you will see a supernova there the night before the next night. However, Ribbon will have a force photometry service where you can plug in your own coordinate and get a flux limit on the data that's available.
Okay, it was not clear to me from the prompt data products that we would be able to do basically a force photometry service.
And would that be subject to the embargo, or would you get force
I believe
photography
it
even
is.
from
I
24 hours?
believe it is unfortunately subject to the 80-hour embargo. We could confirm that, but
this is 24 hours, unfortunately. So I guess the way I was thinking of it, actually, our program will go to 22 and a half because I want to be able to get a spectrum of what we find. And so I had just assumed if I do not get an alert the night before, that it's good roughly down to 24. Obviously, none of this is perfect, but I thought that magnitude and a half of buffer would be good enough to.
that's probably true. And there are probably some data exhaust type products that you could use to sort of, see what was observed previously.
Okay, thank you.
Thank you. And just as a reminder, please say your name before you ask your questions. Yeah. Okay. Yes. Go ahead.
So broader question, I guess, for folks in the room. Dave and I both have DECCAM programs. I know both shadowing LSST at some level, whether it's DECCAT or Dave's program. And one of the primary things limiting us is the readout speed of DECCAM compared to anything with more modern CC readout electronics. Is there some plan for the observatory to update this like they did with the old mosaic detectors at Mayal for MZLS?
That's definitely not a question for me, right?
Yeah, but I figured it was the right people in the room.
What do you think that costs?
Less than a new instrument.
I guess I would, what is the name? The community pipeline, the DECCAM community pipeline. My understanding is that could take, to just detrend the data and get astrometry, does take an hour or two. That is the part that I would like to cut down on a little bit if possible. And that may be more doable than new CCDs.
Hi, Dave. Sam Wine. Oh, you have another one?
I saw you there.
You're talking about following up on daily cadences, but a lot of the data you showed has hour cadence.
I know, man.
You want like these golden sample things, these things that you followed up within hours and have show these blue bumps that are on the like the time scale of 6 hours or so. How do you plan on doing that with something that is at 20-second magnitude?
To get the high cadence data.
Yes.
That will be a challenge. I think we can not get data this good, but I think we could get close with both our SOAR program and, I did not mention, my very close colleague Griffin Hossein Sadeh has a SOAR survey program also to follow up nearby transients with LSST. Not the same program, but sister programs. I think the two together, plus of all our huge collaboration, can put together great data sets. And once we get to about 20th magnitude, that's when Las Cumbres can really kick in and really get super high cadence data. It's that kind of first day there that's really tough, but we will fight to get it. Yeah.
You're looking at nearby things. So.
Yeah, it's very nearby these clusters. Sorry, I should have left it there. And this actually, it says the absolute magnitude depth we'll get to for the DECCAM portion of it, there, which is basically fainter than any supernova has been found before. So
this is Mansi Kasliwal. Dave, I'm your friend. So this is a fun program, and I have better news for you. For anything that is accessible from Palomar's above deck of -35, we will be doing one-day cadence with ZTF on the entire deep wide fast footprint of Rubin. And that'll be in 3 filters, GR and I. And in that footprint, we get to 20.5 mag, but we can certainly for Galaxy clusters go down to 22nd mag with 300-second exposures. So
You should do that, yeah, yeah.
You are
You should
welcome.
copy my project, yeah.
No,
you
no,
should.
this was written into NSF proposals 2 years ago. So
Okay.
yeah, so but it'll be fun, and the data is public. So please feel free to use it and make some fun discoveries.
We definitely use ZTF all the time. Thank you very much.
All right, thanks very much. Let's
Yep.
thank Dave again. And invite Tatiana Acero Cuellar to talk about creating a light echoes data set with the LSST science pipelines.
Okay, hello, I'm Tatiana Acero Cuellar. I'm a PhD candidate at the University of Delaware, and I'm going to talk about creating a light echo dataset using the LSST pipelines. So what is a light echo? So these are the phenomena that we observe when light from an astrophysical event, like for example, a supernova, has been scattered by dust. So light echoes can be like this. So here is 2 light echoes, each one produced by a different plane sheet of dust. And these are light echoes from supernova 9087A, and the video is showing the evolution over time. But light echoes can be like this. These are light echoes from Tycho supernova. Also like this, each black, white cloud, it's a light echo from Eta Carina. So, okay, that was a video. So the video was showing I don't think, okay, it doesn't matter, but it was showing how the light echo is formed. So you have your event, the ejecta is like moving towards the observer, and the light from the event is going to interact with each piece of dust that is on the way. Okay, so why do we study light echoes? So with light echoes, we can study the originating transient. So for example, you saw the light echoes from Eta Carina, and those light echoes were produced by the great eruption that was the first that happened many years ago. And also, for example, Tycho supernova. We can also study the reflecting dust. And finally, with the geometry of the light echo and knowing the distance between the light echo and the source and the observer, we can do a 3D reconstruction view of the source. So how we detect light echoes in optical surveys? So as you saw on the images, light echoes are diffuse, usually very faint. They are time evolving, so in theory you could use DIA, but DIA is designed for point sources, and light echoes are not point sources. So, and besides all of that, light echoes have unique shapes and time evolutions. So you can have 2 very different light echoes from the same source. So they are like very unique, and they are also very rare. So all this means that so far we have detected light echoes by visually inspecting images. And this doesn't scale to large volume of data, like for example, Rubin that is going to collect 20 terabytes of data each night. So, one way or the way to detect light echoes is using machine learning. So there have been works that have like trained machine learning models to detect light echoes, and they perform well given the data set that they have. But the problem is that in general, we don't have enough data that is like that recollects all the diversity of light echoes. So the models are good for the data that you have at hand. So my work is focusing on generating fake light echoes or fake light echo images by implementing a forward modeling of dust and transients to generate synthetic light echoes. So I like to talk about like 4 different ingredients that you need to simulate light echoes. So the first one is to like understand the geometry of your system. The source, the dust, and the observer can be described with an ellipsoid equation. So the light echo shape is going to be the intersection between that ellipsoid and the geometry that you choose for your dust. In my case, I'm always using a plain sheet of dust. Then you need a time component because the source is time evolving, so your light echo is going to be time evolving too. Then you need the source properties, how the source change over time, how it changed with the wavelength, all of that. And then finally, you need the optical properties of the dust. So people that is smarter than me propose those models that reproduce like observable conditions, and they tell you how the scattering properties change. So once you have all like these pieces together, you can like generate the light echo simulation. But then that simulation need to be on a realistic background. So for that, right now I'm using DC2 data, and I'm using the LSST pipeline, specifically right now the version 27. And right now I'm doing everything on NERSC. But today I learned that DP1 is going to be available or soon available on NERSC. So the idea is to move all of this to a more recent version of the pipeline because they change everything, even the names of the images. So the idea is to do that, but we already have the DP1 tutorial, so they already did like the hardest part. Okay. So now I'm gonna show like 3 different cases. So I'm using the light curve from supernova 2011 as my source. And then I have this system where the distance between the source and the observer is 52,000 parsec. That is the same distance as the Magellanic Clouds. And then I have 2 pieces of dust. So the evolution over time of a light echo produced by the first piece of dust is this animation. So the radio of the light echo is going to expand over time. And then I didn't say that, but light echoes are usually detected on different images. So here in the other panel, I have a light echo observed 600 days after the peak of the supernova, then another one at 750 days after peak, and then the difference image. So with a case like this, we can, for example, recreate the light echoes produced by supernova 2011 A, 2087A. Then this is basically the same scenario, but the pieces of those are closer to the source. So the light echoes, I mean, it's hard to tell, but they are like smaller. the pixel size here is smaller than the previous case. And then the final example is that instead of assuming that the piece of dust is like infinitive, you can constrain the dust in just like a region. So your light echo is only going to be this like arc of like, yeah, just this arc. So creating the light echo data set. So I show you 3 examples where I change only where I have fixed the distance between the source and the observer, but I have changed the distance between the source and the dust. I use the same light curve, and I basically use the same dust geometry. But you can also change the duration of the source, the distance between the source and the observer, the optical properties, the light curve of the source, the observing time, the dust model, the wavelength, the observing conditions. So you can change a lot of things. So with this approach, it's possible to create a very rich data set containing light echoes. And that's all. Thank you.
Thank you, Tatiana. Questions? We have time for a couple of questions.
So as you said, the difference imaging pipeline is going to be most sensitive to point sources. So did you ask whether the point source detector would pick up these objects in practice, or how should we think about that?
So I did try to do DI after injecting the light echoes, and if I recall correctly, of course, I didn't get any detection back. But I guess the question is more it's more oriented on how, in real conditions, how are we going to select the images that are going to have light echoes? So I don't have a simple answer for that, or maybe I have a simple answer for that. It's just to check everything. So I guess I don't have a complex answer for that.
Any other questions? Yes.
Extragalactic supernova are too far away to see this light echo in image, right? So what kind of source light echo are you looking for? It's I know, like Eta Carina or some supernova remnant, or any other source you expect to see light echoes?
So Eta Carina was I think a very weird example, a very extreme case. So in general, the expectation is to find light echoes from very bright supernovas. So for example, here I use the supernova 2011 FE, and with that supernova, after this, with the simulation, the light echo has a magnitude of 20, 22. So it has to be a very bright supernova and a close kind of supernova.
Okay, let's thank Tatiana again. We invite Shar to talk about fast transients, discovery, and characterization potential with LSST.
Thanks, Shira. Okay, yes, hello, I'm Shar, and today I'm going to talk to you about fast transients. This work was done in collaboration with Christina, who I heard was in the back of the room somewhere. Hi, Christina. So just so we're on the same page, fast transients are basically anything that evolves faster than your typical type 1A supernova. So that includes a wide variety of different types of objects: galactic, extragalactic, dim, bright, day scale evolution, minute scale evolution, or even less, and all kinds of colors, physical sources, and light curve shapes. And they are a very exciting class of objects because we've been finding more faster ones recently. So I want to introduce you to my favorite plot. where here we have most known optical transients, and on the y-axis we have the peak magnitude, and on the x-axis we have their characteristic timescale, so how long it takes them to evolve. And as you'll see, as we animate filling in this plot over time, basically over the history of astronomy, we've added transients discovered at longer time scales to shorter and shorter time scales, so that one could take this to mean that in the future we will find even shorter timescales of phenomena, and that is an exciting place to look for finding new stuff. So you may be wondering, will we find some of these fast transients with the Vera C. Rubin Legacy Survey of Space and Time? And before this year, we only could quantify the answer for the kilonova, but now we are quantifying the answer for additional classes of fast transients based on contributions from all of you in TVS. I also want to mention that we're responding to the Survey Cadence Optimization Committee's call to action like exactly 1 year ago. They asked the community to try to evaluate the proposed changes to the number of rolling cycles in the cadence, which are going to mean that we sample these shorter periods slightly less often, and we want to figure out what reduction in science that corresponds to. And just so we all know what a rolling cycle is, basically that's when we return to the same part of the sky more frequently during some periods and less frequently during other periods, and then you get the same number of total visits overall. So the way to evaluate this is to make a metric. The SCOC uses metrics to evaluate potential survey strategies. They have like literally hundreds, I think, and these are written by the community. And these are the science cases that you all have helped us come up with metrics for. Today, I'm going to be talking about gamma ray burst afterglows and LF bots. And I want to thank all of our experts who've given us details about these science cases. So essentially, yeah, it's you, Riley. So essentially, for each science case, we're going to simulate an extremely simple light curve. We're going to put it in space. We're going to determine the criteria for the metric, and then we're going to run the metric and analyze the trends and the different cadence efficiencies. So I'm going to walk you through that for GRB afterglows. So like I said, this is like the world's simplest light curve. We didn't even model the rise because it's so fast, we're not going to try to see it anyway. But we have this light curve falling very steeply right after peak and then slowing down, but that doesn't really matter because we'll never see that part of it anyway. So that's our very simple light curve. And then we take this light curve and we put it out in space. We give it an RA, we give it a DEC, a distance, dust extinction, and we use the volumetric rate for how many we think there are going to be. You can see them here. And then we determine our metric criteria. So for our most simple metric for GRB afterglows, we need 2 observations with a signal noise ratio greater than 5 in the same filter, observed like with a time gap in between like half an hour and 1 day. That's going to give us like about like approximately the minimum usable information for that GRB afterglow. But we also would love to see if we can find out a little more about it. So we have another metric for characterization, which is if you can find 4 observations with signal to noise ratio greater than 5 and more than 2 filters with a time gap of 3 to 14 days. So this would allow you to like actually see the evolution of that. And then we have a bonus third metric, which is for spectroscopically triggerable, which is whether our observations also show brightness of magnitude less than 21 within 2 days of peak. So you can run any cadence you want on all of these with all of these 3 metrics and see how it does for each of these criteria. So we did that. So over the 10-year survey, we found 101 GRB afterglows. Woohoo! 79 were characterized, 32 were spectroscopically triggerable. And that was out of 750 events in the full sky, with 537 actually viewable from the southern hemisphere. And to check out why this number is like maybe a little lower than you might want it to be, we looked at the time gap between like when the transient is actually brightest and when the first time we see it is. So obviously, you can see these darker columns here are transients that were detected, and then the oranger ones are ones that are not detected. So there are a lot of instances where we have like it's days on the x-axis. So sometimes there's quite a lot of days in between when it's at its peak brightness and then when we see it. And obviously for those cases, we are less likely to detect these transients. Also, some of them are just dimmer. So if it's dimmer at peak and then it's getting dimmer and dimmer over time, then you're less likely to see that as well. So this is the peak apparent magnitude as injected. And then we compared several different cadences. We compared 4 rolling cycles versus 3 rolling cycles with baseline 4.3.1. And honestly, they were like pretty similar. We also looked at 3 rolling cycles versus no rolling at all from baseline 3.6. And we found that no rolling at all was a bit worse. So rolling is good, but it isn't like crazy different going from 3 to 4 rolling cycles. We also looked at LF bots, which are more populous than GRB afterglows, but they're also dimmer and slightly slower evolving. And what we found for those, looking at the different cadences, actually turned out to be pretty similar. So the rolling cycles do help. 4 roll is slightly better than baseline, but not like crazy better. And baseline versus no roll, again, like some rolling is good. So in summary, we are making metrics for fast transients, and preliminary results for GRB afterglows and LF bots show like a low-ish number of detections, but little change between proposed cadences. So that is what we've got for you today. Thank you.
Thanks for your talk, Shar. Questions from the audience?
So you require 2 detections. First of all, this is Dan Purley from LGMU. So you require 2 detections in the same filter to count it in your statistics. Is that right?
Yeah.
Is there a motivation for that? Since I know some of the proposed plans for the rolling cadence, the 2 observations the same night are in different filters.
Yeah.
So is there a reason to require them to be in the same filter?
Yeah, so 2 observations in different filters means you can get the color, and that's important. 2 observations in the same filter means you can actually see whether it changed in that filter in brightness. So if you have a transient that's super fast, like these ones, you would want to compare the same filter and not different filters.
Yeah, but there might be follow-up surveys that could get that observation for you once you have the candidate, a red source in the galaxy. So you might consider not limiting yourself to that and also seeing how that affects the numbers.
Yeah, we could say if you find 1 data point of this event, then we found it, but you probably wouldn't do anything with that if you only found 1 data point. So we were trying to limit it to like something that might plausibly be useful.
Well, it'd be 2 data points, just one in a different filter.
Yeah.
And then you'd have a non-detection the previous night and later on.
That's true.
So you'd have some more.
Yeah.
Other questions? Yes.
This is Igor Andreoni. I'm just curious if you did or you're planning to check out how these metrics perform in the deep drilling field.
Yes, so the deep drilling fields are pretty small. So when we looked, they didn't we injected them over the whole sky, and we didn't particularly return more over the deep drilling fields because they're pretty rare. So there are like a couple in there, but not a big change. Yeah.
Other questions? Maybe I'll ask a quick one. So did you think about, or are there particular sources for which you think would be very difficult to identify with just 2 detections? And if so, then have you thought more about how changing cadence could could help.
Yeah, it's hard to identify like most things with two detections. So really like you do want to be able to follow up, but with two detections, you can see like, oh my God, this object got way brighter. And really we want to see like, will we be able to get that initial like, oh my gosh, this object got way brighter for all of these objects over the 10 years. Yeah.
Thank you. Are there any questions on Zoom? Okay. Okay. If not, let's thank Shar once again.
Thanks.
Invite Xiaolong Li to talk about recovering the light curve of Ada Carena's great eruption through light echoes.
Okay. Hello, everyone. I'm Xiaolong Li, ISST Catalyst Fellow at Johns Hopkins University. Today, I want to share with you some my study about the specific case for light echoes from the Ukraine. We've learned from Tatiana's talk that light echoes are the reflections of the transient event, and if dust on the same ellipsoid will reflect the light that arrives the Earth at the same time. And as light travels, the ellipsoid expand, and we observe the circle expanded outward the original event. And because the light reflected from the dust arrives the Earth at a much later time than the original event. So this gave us a second opportunity to study historical event. And the target that I'm currently studying is the Eta Carinae, which is probably the most massive star system in our Milky Way galaxy. And Eta Carinae underwent a great eruption that eject about 20 solar masses. That's in the 19th centuries, last about 20 years. And the only observations of the great eruptions is the visual estimations of the changes of the brightness recorded by astronomer John Herschel and several others. The plot shows the historical record, and we can observe that there are about 3 peaks and 2 peaks separated by about 5 years, and the second and third peak about 2 years. And now, thanks to the light echoes, we now have the second opportunity to study the Eta Carinae's great eruption using modern telescopes. And the image shows that the light echoes from Eta Carinae observed using the dark energy camera, and the Eta Carinae is on the top left. And if we select specific locations and keep track of the changes of the flux at specific locations, we will be able to recover the light curves of the great eruptions. And if we combine multiple light curves from different locations, we'll get more detailed light curves. And because the distance starts to reflect the light from the early phase, we can recover the early phase from the distant light. dust, and the nearby dust reflect the late phase light. So we from those two nearby dust, we recover the later phase, and combine all pieces. We now have the full 20 years light curves from the great eruptions. And on the recovered light curves, we can observe clearly that there are three peaks, and which is in very good agreement with the historical one light curves. And we even observe a first peak. And we have when we combine multiple filters that this plot shows the light curve recovered in I band and G band. We observe that the third peak in I band is much higher than the first two peaks compared with the in G band. This indicates that there is a strong evolution during the great eruptions. And when we plot the color plot, G minus I plot, we can observe that the magnitude changes about 1.5 reddening. This provide evidence for the mass ejections and dust formations during great eruption. And given our recovered light curves, we can now simulate the light echoes from the East Korea for LASST data. The right shows the examples of one piece of the dust that we simulated for the 10 years that the LASST will observe in the coming year. And the LASST will observe the first peak, and we are excited to look at that. Yes, and then the Rubin LASST, besides the East Korean echoes, Rubin will be first time to a complete series of the light echoes in the south skies, including the East Korean, the crab, and several other historical transient events. And even more, the Rubin may even discover mystery unknown historical transient. And we have developed the full pipelines in preparation for the Rubin's coming data, including the AI-based detection model and the spectral identification and the light curve model and dust modeling. Those will equip us pretty well to study light echoes in the Rubin LASST area. Yeah, I think that's all. Thank you all very much.
Okay, questions from the audience? Maybe I'll ask a quick question. Do you have an estimation of the rates of these mystery echo objects that you alluded to? Yeah, or yeah, some rough estimate of how many you would detect with Rubin?
Yeah, we are working on combine by calculate by the geometry of the historical event and the Earth, and calculate areas that will possibly we can discover echoes.
So Ekaterina's region is rich with a lot of dust, right? So we already have a number of light echoes that surround the object. With LSST, we'll likely get a lot more. You showed one region, but there will be more regions of dust that will light up. Can we study the symmetry of the explosion? Can that tell us something of the eruption? Can that tell us something about the mechanisms of the eruption? You know, it's a triplet star, and there's models that show a clash of one of the components into the wind of the primary massive stars. But the models are still a bit uncertain. Would symmetry help us constrain them?
Yes. By study the by if we can discover the light echoes from the different directions, we can have a three-dimensional study of the transient events that we can study like by taking the spectra, study the difference of spectra in different directions of the light echoes. We can study the symmetry of the event.
One more question.
Thank you for interesting talk. I have question about the AI-based detection. So for the point sources, it is easier because we make these small snapshot and we can put the input data as an input data. But for the some not point source, very complicated shaped feature, how I cannot imagine what kind of data would be input data for the AI. So can you give me more details about this detection algorithm?
Yeah, for the light echoes, because the shape of the dust is very different from each other. But so currently we have a very small data set that is have from the Tigers and the Ithacarinas and the current computer vision models can have able to discover such patterns, and we also try to simulate like this one, try to from our light curves and observe the dust, we can simulate the different scenarios. If we inject the light curves from that have the different lifetimes, we can observe, simulate the dust, that simulate the light echoes that both have extended features or very short features. And yeah.
So large size of the cutout would be the input data, is that correct?
Yeah, by injecting different shapes, we will have a diverse input data set for the AI model.
Let's thank Shalong once again. Next up is Dan Purley speaking about orphan afterglows and dirty fireballs with Rubin Observatory.
Yeah, I think you can.
Okay, great. Well, thanks for the opportunity to speak here. So I'm going to be talking a little bit about the same thing that you just heard from Shar a couple of presentations ago, but in a little bit more detail focused on afterglows and specifically types of afterglows that are new to us and interesting and tell us new things. So first of all, for those who don't work in the GRB field, let me give you a brief primer on GRB's afterglows and why they are interesting. They are manifestations of relativistic jets producing collapsing stars that are shocking the material around them. First, we have gamma ray emission coming from shocks internal to the relativistic ejecta itself, and then shock in the external medium that produces emission across the entire electromagnetic spectrum. Characteristic values associated with this relativistic outflow are 10 to the 51 ergs of energy beamed into a cone of radius about 10 degrees and an initial tolerance factor of about 300. And the observations that we get follow from those properties. Specifically, these lead to afterglow rise time that is extremely short because of the Doppler boosting from these very high velocities of just a few minutes before the external shock is created and becomes very bright. And then following that, it essentially just decays as a power law. First it's about T⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ And that's what we see in a typical afterglow. But that's not necessarily the only type of thing that's out there because, of course, these are beam phenomena. It should be possible to see them off axis. They should be happening off axis. And if you observe it off axis, you won't initially see the gamma rays, but as the emission spreads and the Doppler factor goes down, as it slows down, you will see a signature at late times. Additionally, it has been theoretically predicted that one can get jets that do not accelerate the material to quite the same velocities, but nevertheless you have similar energies and similar beaming factors. These will produce afterglows that are just as luminous, but they'll take longer to rise. And so in addition to the kinds of afterglows that we know about with the purple curve, there might be these low Lorentz factor afterglows, which are sometimes called dirty fireballs, which have similar light curves, but take a longer time to rise, hours instead of minutes. And then there very much should be off-axis afterglows that actually take days to rise because we don't see them until the jet has really slowed down quite a lot and is beaming in all directions and no longer boosted along the line of sight or the line of ejection. Okay, so we'd like to find these. It's easy to find gamma ray burst afterglows if you have gamma ray burst satellites. It's not so easy to find things in the optical where the sky is crowded and the phenomena are fleeting. But we've been looking because it would be very interesting to find them to better measure the true rates of these phenomena, characterize jet structure, characterize the characteristic velocities of outflows, and better understand acceleration of jets from collapsing stars in general. So we've been looking with many facilities, including in particular this Wiki's transient facility, which I've been working with a number of people, including in particular Anna Ho, on finding them. And these have been, I'd say, moderately successful. There are 8 orphan afterglow candidates, which is to say optically discovered afterglows that are definitively cosmological, show relativistic evidence of relativistic motion, but don't have accompanying gamma rays. So we know we can find them, but we don't have enough, and they're not sufficiently well characterized to say definitively whether the ones that we have found are simply afterglows that were out of the range of being triggering higher energy satellites or genuine dirty fireballs, and we do not have any off-axis candidates except for maybe one ambiguous radio counterpart. So we'd like bigger and better facilities, and of course Rubin is very much one of those, and it is now here. You can come up with whatever figure of merit you want, but in terms of the number of things it can find in the universe, given its field of view and depth, it's an order of magnitude improvement over ZTF, and so naively you might expect to find roughly 10 times as many things in the same period of time. In addition to that, it's going to do a lot of other great things for afterglow searches, including producing very high quality galaxy catalogs and photo-seq catalogs, which will help us separate nearby universe things like flaring stars and young supernovae from distance universe relativistic things much more easily than in the past. Okay, so that's going to be great. So what exactly is it going to do? What kind of rates can we expect, and what will we learn from then? Well, we won't know until we really do it, but I tried to come up with some basic projections for what can be done given what we know about the current afterglow population and some basic characteristics of the wide, fast, deep survey. And so this is a big table here, so I'm not going to go over all the numbers, but what I'm trying to do is to say, okay, this is how frequently we will expect to observe an afterglow from the known population, from the known satellites that we have, extrapolating over the whole sky within a certain period after the explosion. So within an hour of explosion, we expect about 1 per year of those is going to be observed by Rubin, and they're typically going to be about 20th magnitude at that point. But there will also be many more afterglows that are observed within about a day, and those will still be detectable to Rubin. And then of the brightest afterglows, you can observe those for much longer. We'll find them later, and we'll be able to learn more. I'll explain this more in a second. Okay, so let's focus on a few example cases and what kinds of data that they're going to look like. So this is the typical case. The typical case, of course, is things towards the faint end. This is going to be, as a rough minimum, 25 per year based on the known population. But if there are dirty fireballs out there that we're not currently finding, if there are GRBs fainter than the population that we know about, we might find more. But we should find about at least 25 per year if we're able to identify them in the data stream. They're not going to be easy to find. They'll be single night transients. They'll be there in both exposures, but we'll have to cross-match them to galaxies to determine them. But if we're able to do that effectively, we'll be able to measure the numbers of these things across the sky, compare that to what we infer from GRBs, and do some statistics to see that there might exist afterglow populations beyond that's currently known. Okay. But we won't be able to distinguish dirty fireballs on an individual basis that way because we will not be able to sample the actual light curve structure. Okay, but as Dave alluded to in his talk, you have the demographics of the whole population, but we also have fewer and better observed brighter ones. And so here's an example of a bright afterglow. There won't be as many of these, but there will be about 5 per year that are observed within the first night or two after explosion. And because they are bright at first detection, there'll be several detections along the Rubin light curves. It'll be possible to characterize in reasonable detail, and even better, these will also be bright enough at peak to be detected or have constraining limits placed on them by other surveys, in particular ZTF, which, as Monty mentioned, is going to be co-observing the same regions as Rubin, but also other surveys like LS4, GO2, and so on. And so we might actually be able to distinguish dirty fireballs from ordinary afterglows on an individual basis by putting them together with those facilities. And then when we're lucky, perhaps once a year, we will have a very exceptional bright afterglow, which we'll get loads of data on and can do this even better. And okay, 1 per year is not a great rate, but what's actually interesting about that is for every one of these exceptional afterglows, the brightest afterglow in a given year, there should be approximately 10 times as many similar events that are pointed a little bit off axis. And those actually are going to be bright enough at late times that we will be able to see the off-axis rise and decay and pick those out from the population to determine the true off-axis rates of afterglows with LSST. But we will have to distinguish them from supernovae, which is challenging because these are no longer fast transients. They'll be mixed in with the supernova population. So we will have to do some very clever color and luminosity selection to identify these things. But it should be possible. So to summarize, Rubin and LSST should be able to find over the 10-year survey hundreds of orphan afterglows to be able to constrain volumetric rates. And if we find those rates to be higher than what we expect from current afterglows, that's one inference of a additional population of dirty fireballs. There should be dozens of afterglows that are brighter and complementary to high cadence shallow surveys, which we can use to constrain rise times and Lorentz factors directly. And there also should be eventually, if we're able to pick them out from supernovae, off-axis afterglows. And with all these things together, I think we have excellent prospects of getting a more complete look on the afterglow population in the universe.
Dan, questions? Any questions from the audience? Yes.
Hey, Dan. Great talk, Thomas here. You mentioned the last part that the challenge will be to distinguish those slow rising alpha-axis afterglows from supernova. What do you think could be the tools that have you thought about how we can sort of distinguish, because they will be super faint.
So it's a double challenge, right? So one challenge is that the timescales are pretty similar to supernovae, so about a month. And the other challenge is that GRBs are accompanied by supernovas, so there'll actually be a supernova light curve in there on top of the afterglow in some cases. So I think it's the colors that are going to do it, because these are slow enough that you do get, depending on the exact filter rotation and what's decided, you do get a whole suite of colors, including U-band, which supernovae are very faint in at most at later times, as well as the redder filters. So I haven't tried to do this yet in practice, so I'm not going to say it's going to be easy. But with the filters and with complementary multi-wavelength observations, if we're able to even get some candidates and get X-rays and get radio, that should be the way to distinguish them from ordinary supernovae.
Thank you.
Other questions? Other questions on Zoom? Okay. If not, let's thank Dan once again for a very nice talk. Thank you very much again for coming to the Transit and Variables session. I had just one quick reminder, which is that tomorrow is the unconference session, and there are some TVS, Transient Variable Star related topics that have been proposed. So please go over there, look at the sessions and vote for them so that we can have an unconference session. And now is the group photo. All right, thank you very much.